Salutations to all. You can call me Cuddy or Mystery Extravagant, cause I'm keeping my money. When my doors are swinging, it's like a bird on wheels. Come to.
Hi everybody, here's your limits 3 ways video. We're going to be doing limits graphically, numerically, and algebraically. All 3 ways are needed on the AP exam. We're going to start with graphically first. Now keep in mind that these are your notes, so I'm not going to be standing in class talking about this while you copy it. This video is replacing all of that. The video is going to be anywhere from 10 to 12 minutes. As you go through it, it might take 20 to 25 minutes to write it down, so just be aware. And any questions that you have, just put a little star in the side of your notebook where you had the question, and then you can ask me the next day in class, and I'll be happy to answer any questions you have after you watch the video. Okay, so we're going to be dealing with this function x cubed minus 8 over x minus 2. And we're going to want to find the limit as x approaches 2. Now, just looking at this function, this definitely looks like it's going to be a rational function with a variable in the numerator and the denominator. Rational functions usually have asymptotes. You did those the last 2 years in math class. But let's see what happens when we graph it. Now, just keep in mind, we want the limit as x approaches 2. So if this is 2 on the x-axis, we want to know what y value we're approaching from the left and from the right. So what y value does the function approach when x approaches 2? Keep in mind this is x, the limit will always be a y value. Another way of thinking of this is what does y intend to reach? It might not actually reach the value, keep that in mind. It's not like when you do a limit, the y value has to be reached by the function. It might not reach it, maybe because there's a hole there or some kind of jump discontinuity. All we care about is what is y trying to reach. Now, whenever we do a limit, you should always do substitution first. I'll be saying that over and over again. And for substitution, that means you're going to take 2 and you're going to plug it in for x. Now, if you plug 2 and just do it in your head real quick, that would be 8 minus 8 over 2 minus 2. So that's going to give you 0 over 0. That is what's called indeterminate form. It's a very important vocab word here. We're going to be using that a lot throughout the year. Indeterminate form. That, again, that means 0 over 0. If you get indeterminate form, you can't find the limit. You have to fix it. 0 over 0 really means that there is a hole in the graph at the x value that you plugged in. So at 2, I know there's something going on in the graph. Some kind of hole is there that the graph is not going through. So right now, the function is undefined at x equals 2. Now we're going to fix this, but before we fix it algebraically, let's look at what's going on graphically and numerically first. Got your grapher out with you? Pull it out now here. You don't want to watch me have all the fun. Graph it with me. So x cubed minus 8 over x minus 2. Don't forget your parentheses around the numerator and denominator. I'm going to do zoom standard first when I graph this, and this is definitely not rational looking. I don't see any asymptotes. In fact, this kind of looks like a parabola. We're going to see exactly what's going on soon. Now, if I look at 2 here, and I go straight up, I'm kind of almost going off the edge of the graph here. So I don't really need to go to -10. Let's just go to -5. And for my y min, let's do -5. And for the y max, let's do 15. That way we can see the graph a little bit better and see what's going on at 2. Okay, so again, we care about what's happening as we approach 2 from the left and as we approach 2 from the right. So let's go ahead and trace this and see what's going on. All right, find my cursor here. So cursor from the left, and I approach 2 from the left. It's important you keep your directions clear here. I'm coming from the left and I'm getting closer and closer to x being 2. Notice what's happening to your y values over here. So y is getting closer and closer to a certain number, maybe, we're going to find out. So I'm at 1.25, 1.7, 1.9, that's pretty close to 2. I'm at 11.595. Oh, I went past 2. Okay, so now let's go from the right. So I'm moving my cursor onto the right, and I'm approaching 2 from the right this time. So I'm getting closer and closer to 2. Oh, I'm at 2.04, coming from the right again. I'm at 12.27. So as close as I get from the left, I'm 11.5. as close as I get from the right, 12.27. So I can guess my limit might be 12 because that's in between those two y values that I had. So let's go ahead and sketch this here. On the graph is that we know that there's a hole at 2 because when I plugged in 2, I got 0 over 0 in determinate form. But the graph doesn't look like there's a hole in the graph when I'm at 2. The only way you can force the graph to show that is if you were to adjust your window and zoom in a lot, which it can do. But just realize that when we graph this here at 2, we're just going to make sure that we draw a hole in the graph. So if I go up at 2, 4, 6, 8, I'm guessing it's 12 right now. We're going to verify that soon. And just approximate a parabola like this. Doesn't have to be perfect. There we go. Let's see here. I'd make this note. If we trace a function close to x equals 2, we can see the y values are approaching 12. So we're guessing right now that the limit is 12. We're not very accurate though because we didn't actually get exactly 12. So we're not really happy with this because we want more accuracy. So we're going to try numerically next, and then for the ultimate accuracy, we're going to do algebraically. So make sure all this is written down. Okay, numerically, this is method 2. Numerically just means you plug in numbers, you look at a table. Now we're going to use a calculator to help us evaluate the limit numerically because we have numbers that are not very nice to plug in, definitely not by hand and not by typing this in over and over again. Now because we want to know the limit as we approach 2, I have x values getting close to 2 from the left and close to 2 from the right. So I'm going to show you 2 different ways you can evaluate quickly on your graphing calculator. You might know one or both of these. If not, you're going to want to start doing these soon to help you save time. First thing you can do is, let's say you are just looking at the graph here and you hit trace. If you want a y value for when x is 1.75, rather than going to, like the alternative would be to go to your home screen and do 1.75 cubed minus 8, type that in over and over for every x value, and that's extremely tedious. So if you hit trace and just do 1.75, enter, you're going to get the y value right away. Another way you can do it is if you do alpha trace, you'll get y1 here. Basically, you want the y of whatever your function is plugged into. So like my function is plugged into y1, so I want to call up y1 here. And this is just function notation. It's saying, hey, what x value do you want me to plug into y1? And you're going to tell it. And it can do it like that as well. So 10.5625. 10.5625. All right, at 2, we're undefined, so I'm not going to put anything there. What I want you to do is use your grapher to evaluate these other 7 x values very quickly, either using the trace or the y1 feature, and then come back. Make sure you're actually doing it so you can see what's happening to your numbers. All right, so you should have gotten these y values, and it's very clear whenever you look at this that as you come, so here's 2, as I come from the left, my y values are getting closer and closer and closer to 12. As I come from the right, again, I'm getting closer and closer and closer to 12. And again, we're going to go ahead and say we think the limit's 12. We're pretty confident right now. Again, we didn't exactly get 12 yet, but we got really close to it. So as we approach x equals 2 from both sides, it looks like y intends to go to 12. Even though it's undefined at the table and in the graph at 2, the numbers are still getting close to it. So even though it's not going to actually reach 12 because it's undefined, it's getting close to it. Once that's written down, we'll move on. The last way is algebraically. So algebraically is when you're going to get the exact answer, and you're going to use actual factoring algebraic techniques. We want to verify the limit is 12 without using a table or a graph, because on an AP exam, sometimes you're going to want to be able to find a limit really quickly without having to graph it or plug in really elaborate x values. So we're going to take this here and we're going to try and get around the fact that we got 0 over 0 at first. We're still going to do direct substitution, but we don't want to end up with 0 over 0 again, because when we first tried it, we got a 0 and a 0. So we're going to have to do some algebraic manipulation. And if you look at your numerator, you might recognize this from Algebra 2 to be a difference of 2 cubes. And if you don't recognize it, then hopefully this is a refresher for you. And don't tell me you've never seen it. So for a difference of 2 cubes, each of these has to be a perfect cube, meaning you could do the cube root of it. So A can be identified as x, and b can be identified as 2 because 2 cubed is 8. So I'm going to plug x in for all the a's here, and I'm going to plug 2 in for all the b's. Whoops, that was a b right there. Okay, so whenever you do that, you end up with this factored form. And let's practice our wonderful limit notation. I have the limit as x approaches 2. Let's go ahead and replace our numerator with our new factored form here, like so. And look at that. I have the exact same factor in the top and bottom, connected with multiplication here, meaning I can freely factor, no worries there. And check it out, I don't have a rational anymore, I have a quadratic. Not really a surprise because when we graphed it, we got a parabola. The y-intercept is 4. This is ax squared plus bx plus c. I'm struggling. Oh, I'm making it worse. Anyway, that's a 4. Okay, notice that every time I did this, I wrote limit. We're not going to be lazy here. We're not going to use bad notation. You write limit all the way until you point to the point that you would substitute. You know for yourself here that we're going to try direct substitution again now that we got rid of the problem. The problem were the shared factors. Now that we canceled the shared factors, our 0 over 0 is gone because 2 minus 2 and 2 minus 2 are both 0. They're gone. Just have this. When you plug in, all I did was just quickly plug 2 in for every x, and 2 squared plus 4 is 12, which is what we thought from the beginning. So yeah, like I was saying, make a note here. We're going to try direct substitution again, and then once you substitute, you don't need to write the limit anymore. And the limit is going to be 12 no matter how you do it. So make sure you have everything written down here. Go back if you need to get anything that you missed, and we'll be practicing this in class and for homework. See you later.